So we should get started with our, as we normally do, a multiple choice problem. I hope some people have had a chance to try this one. We have a vector 3, 2 and another vector 2, 1. And we're told W is this other vector. And it satisfies the following. If you project W onto U, so this is one thing we learned last time, how to do projections, you get back U. So remember, whenever we project onto a vector, it's a multiple of the vector. So that says, oh, this projection is just U itself. And if you project W onto V, all you get is V. Then the question is, well, what's W? There's some options: 5, -1, -1, 5, 7, -3, 11, or no such W exists. Anyone have an answer? The answer is D. There is, in fact, such a W, and it's -3, 11. Now, how would you solve this? Well, the first thing is to say, well, I have a formula for projection, so let's write down the formula for projection. I know that the projection of W onto U is this U dot W over U dot U times U. But I know the end result is U. That tells us something. It says, hey, this part in front better be 1. So that leads us to saying that U dot W is U dot U. Well, if we call W a name temporarily, A, B, for example, then that leads us to a relationship. So U dot W, 3A plus 2B. And then U dot U, 3 times 3 is 9, 2 times 2 is 4, 9 plus 4 is 13. Same process. We do the projection of W onto V, you get another relationship, 2A plus B equals 5. Now at this point you have sort of two options. One option is you say, I'm just going to solve it like this is a long form problem, which is fine. You say, what do I have? 2 equations, 2 unknowns. You look for ways to combine, solve for A, solve for B, and there's the answer. But there's another way to approach this, which is to say, you know what? I don't have to always work it the long way. I just have to have enough to rule out options. And what can we do? Well, once we get to here, we say, well, I have relationships for A and B to satisfy. Instead of doing this computation, I just check. Well, 3 times 5 is 15. 2 times -1, that's -2. 15 minus 2 is 13. Well, what about this one? 10 minus 1, that's not 5, it's 9. So it's like, okay, that's gone. And you can just work your way through. So you will have to, at some point, start thinking about, like, okay, how do I prepare to take these multiple choice problems? You know, what's the right way to do it? And you have to do it a little bit differently if you want to be optimal. But you're engineers. You're very good at optimizing. So I believe in you. All right, so that was our warm-up problem. Okay, so today, no quote, rather a learning technique. So this is something they teach, well, I don't know if they teach it, but they do it a lot with computer programmers. And it's called rubber duck debugging. And it involves a rubber duck. So imagine that you have a rubber duck. So I happen to have some rubber duck here. And we'll put the rubber duck over here. Now, what happens? Well, people get stuck. They have problems. Those are what you call your bugs. And how do you get unstuck? Well, the worst thing to do is just sit there and twiddle your thumbs. That doesn't help very well. So what they say is, like, do the following. Talk to somebody, and if you don't have somebody to talk to, have a duck nearby and start talking to the duck and explain what the program is supposed to do. Step by step. I want to do this, so I'm doing that, which does this, and this is the result. And by talking through what happens, the programmer says, I know what's going on. I know how to fix it. It's the same with math. If you're stuck, try explain why you're stuck. And you can talk to a duck. and hopefully you have a duck that you like to confide in. But for an even better effect, try a person. And, there's a lot of people taking this class, and I would strongly encourage you to work together, and I think it's one of the best ways to learn is to talk and communicate and say, hey, what's going on? Let's figure things out. The best way to learn is to teach. That's why I feel like I'm finally starting to get the hang of calculus nowadays. It's only taken me a little bit of time. But the good news is, you're smart. You're going to catch up quickly. All right. So, goal for today is to talk about multiplying vectors. And ultimately, there are 3 ways to multiply vectors, and we know 2 of them. So when I say multiply here, a multiplication where a vector is involved. So one thing is scaling. So scaling is when you take a number times a vector. And the end result, when you scale, is a new vector. Say, okay, great. Well, what is scaling good for? Well, one thing that you can do with scaling is that you can check if things are parallel. Now, parallel says essentially they're pointing in the same direction. But in terms of this idea of scaling, things are parallel if one vector is a multiple of the other vector. So you can check, okay, can I scale one vector and get the other vector? And if the answer is yes, parallel. If the answer is no, not parallel. You can also turn vectors into unit vectors. We like unit vectors. They're our go-to for describing direction. Okay, so that's scaling. Last time we talked about the dot product. Now the dot product says, take a vector and another vector, and then there's this thing called dotting, which produces a number. And here's an example, 2, 1, 4, dot, -5, 2, 1. Well, I gave the end result. How's the process work? Well, the process works, you multiply the corresponding entries. -2 plus, -10. I know how to multiply 2 times 5. -10 plus 2 plus 4. And that's a number. Now, what do we do with this number? Well, it turns out there's this nice fact that if you took a dot product, it's the magnitude of u, magnitude of v, cosine theta. So one thing that this allows us to do is it allows us to find the angle between vectors. But really it says, hey, anytime you can get a cosine relationship involved, where cosine is the angle between your vectors, dot product can be very helpful. So in particular, we saw this idea of projection, where we have a vector. Let's say v is here, u is down here, and we want to project v onto u, which is this sort of portion of v that points in the direction of u. Well, that can be done very simply using projection. It also is a great way to test orthogonality. Orthogonality means theta is 90 degrees. So if you ever want to test orthogonal, you say, check the dot product, is it equal to 0? And it's a yes-no question. Yes, orthogonal. No, not orthogonal. So these are 2 ways. Now I'm going to make a comment here. Scaling works in any dimension. Dot product works in any dimension. We're now going to do one last product. And spoiler alert, the reason I mentioned any dimension is that it won't work in any dimension. It has to have a very specific constraint. So it's called the cross product. And what's the idea? You're going to take a vector, cross a vector. So this is the notation. See how before we had a dot? Now there's a cross. Vector cross a vector, and out comes a vector. Now, we're going to go through and explain it, but I want to just emphasize for right now a few things. This only works in dimension 3. Now, you might say, well, what's interesting about dimension 3? That's actually a good question. It turns out 3 has this really cool property called 3 equals 2 plus 1. And that is why it only works in dimension 3. Now, you might think I'm being silly, but that's actually the truth. The fact that 2 plus 1 adds to 3 is the reason it works in dimension 3, and no other dimension can have anything that works. Okay. So I want to say a few things you can do with the cross product. The punchline here is that this can construct orthogonal vectors. So we talked about how the dot product can test orthogonal vectors. This can construct orthogonal vectors. And the other thing is that the magnitude of this cross product, so if I take U cross V and take the magnitude, it has a similar thing to the dot product. It's the magnitude of U, magnitude of V, sine theta. In fact, we're almost done defining what the cross product is. Because if we have a vector, it has two things. What two things make a vector? Magnitude and direction. I just told you what the magnitude has to be. So now, if I tell you what the direction is, then that defines the vector. Okay. So, let's talk about direction. All right, so where does the direction of U cross V come from? Here's the idea. We want to have it so that the new vector, the output vector, has to be orthogonal to or perpendicular to U, and it has to be perpendicular to V. So in other words, it's perpendicular to both the inputs. So that's why I said that this cross product is very good at creating orthogonal things. So if you ever have a problem that says create something perpendicular, ... It's like, creating perpendicular things, that's the cross product. Now, let's think about what's happening in our three-dimensional space. So we're in three-dimensional space, and we put our vectors together at the end somewhere, doesn't really matter where. And we have U, and we have V. Now, if you think about how U and V relate to one another, there's an observation, which is they're essentially sitting in a common plane. So if you put their tails together, you have that the ends, you got 3 points where their tails combine and their end points. So there is somewhere sitting here a plane. Okay. So U and V are in some common plane. Now, I want to be perpendicular to U, and I want to be perpendicular to V. So I want to be perpendicular. I want to be coming out at a right angle. So I'm perpendicular to both U and to V. Now, is that enough to uniquely determine direction? Well, essentially almost yes, but no. Why almost yes? Well, how many dimensions do you have in a plane? 2. There's your 2, right? I mentioned 2. So how many directions are perpendicular to the plane? 2. Perpendicular to the plane, not 1. Because you're in dimension 3. So once you have your plane, just think of the plane as the XY plane. I want to be perpendicular to the XY plane, so I have to go up, right? So, if I know I'm perpendicular to both U and V, is that enough to tell me the direction? And why not? And how do I fix it? So, there's a series of questions. Is that enough just to say I'm perpendicular to both U and to V? No. Good. The answer is no. Excellent. You're cracking this code. All right. Why not? Because it could go in one of two directions. We want one direction. So we have to make a choice. But somehow we have to have a choice which is consistent. So we need a rule to follow. Something that might be very handy. Something right near us that could be handy to help us. So, is there anything available to help us break the tie, to know which way to go? Right hand rule. Okay, good. So it's perpendicular to you, perpendicular to V, and we obey the right hand rule. Now, the good news is you don't have to stress about the right hand rule. We're not going to go into that fine a detail. What we care about are two things. The fact that it's perpendicular to what you start with, and it has a nice magnitude. We're going to talk about why the magnitude is nice. Now, in case you're wondering what's the right hand rule, it involves a right hand. And hopefully you have one available. If not, become friends with your neighbor. And maybe they'll let you borrow theirs for a moment. And the idea is, when you're doing U cross V, you see how your hand has this like bendy part? That you can bend it here? Well, you have to imagine that these finger parts go where U goes. And this part here, so this is where U is. This is where V is, and you want to be able to like close your hand. And so like your fingers don't bend this way. So that's why you break the symmetry. So here, UV, that would say that in this particular diagram, you should be going up. That's the one you want. So that's what the right hand rule says. All right. So that's all you need to do the cross product. Now, that's all you need geometrically. Let me ask a quick question. What happens if we switch the order?
It goes the other way.
Yeah. It's not a left-hand rule. It's still the right-hand rule. But what do you have to do? You have to go in the opposite direction. So you get a negative sign. So this is one of those things like what? But you're getting that negative sign. Essentially what's happening here is it's a reflection of the fact that there's an orientation involved. And negative signs, I oftentimes, when I think about calculus, I think of negative means orientation. Now there's a couple of other interesting quirks. What happens if you take a vector cross with itself? And for this, I'll remind you of a fact that when you cross a vector together with another vector, you should get magnitude of u, magnitude of v, sine theta. What comes out? 0. Now 0 the number? 0 the vector. Now why? Well, what's the angle between a vector and itself? 0. So what's sine of 0? 0. So the magnitude has to be 0. There are not very many vectors with magnitude 0. So it has to be the 0 vector. So again, it's kind of strange. It takes some time to get used to. So let's talk about 3 very nice vectors. We've mentioned these before, and these are our I, our j, and our k. So those are unit vectors. Now, what's nice about I, j, and k? They're all perpendicular to each other, because they point in the x direction, the y direction, and the z direction. What else is true about I, j, and k? They all have magnitude 1. So they all have magnitude 1. The angles are always right angles. So if I look at their cross product, the magnitude is always 1. Now that's good. That says really when I take I, j, or k and I cross it with one of the others, I'll get numbers out. So I'll get nice vectors out. So we have I cross j, I cross k. We'll do a quick j cross j, j cross k, k cross I, k cross j, k cross k. All right. So we know already I cross I, j cross j, k cross k, those are all zeros. What about I cross j? So I, j, where's your thumb pointing? It's pointing straight up. So I cross j is k. What about j cross I? Negative k. Okay, well, let's see, what else can we do? How about j cross k? What's j cross k? I. So k cross j is negative I. All right, how about I cross k? Let's see, is that a good one? Or maybe k cross I is a better one. Yeah, k cross I. It's j. I cross k is negative j. So we know how to take I, j, and k. Now there's one other nice fact I should have mentioned, and I'll mention it now, is that cross products respect distribution. So that's just another way of saying, oh, I can do the following. Let's see. If I have a vector, ai plus b times j plus c times k, cross di plus ej plus fk, I feel like we're doing alphabet soup today. What we can do is we can then start expanding. So we can do ad I cross I. Then we can do ae I cross j, and similar, so forth and so on. Now, I'm going to skip the steps, but if you want the steps, they're in this handout, right? You just take this distribution here. You expand it. We know what's happening with I cross j, I cross k. And so if you follow your nose, you get to the following expression. So in particular, I like to write things in component forms. ABC cross DEF is equal to, and I don't have this memorized, but that's okay, you don't need to. BF minus CE, CD minus AF, AE minus BD. So this is a way to take a cross product if you memorize this formula, but don't memorize this formula because that's too hard to memorize. We're going to teach you a different way to do it. All right, but the punchline is there's a formula. We started talking geometrically, we got some basic properties, and then the basic properties said, okay, what can you do with vectors written symbolically in this composite form? Okay, how do we actually do this? How do we really take a cross product of two vectors? Well, here's our actual method. Take your vectors, and we're going to make a little 3x3 determinant. Now this involves a matrix. So you're going to fill up your matrix. In the top row, you write I, j, and k. What do I, j, and k represent? The I, j, and k vectors. Row number 2 is your first vector. And you just write it down. A, B, C. And then the last row is your DEF. So you fill in the matrix. All right. Now, my claim is we're halfway there. Next step is you need to take the determinant. Do you remember determinants? No. Have you ever learned determinants? Okay, some people said yes. Some people are like, I don't know what that means. But okay. Well, if you haven't learned it, now's a good time to learn it. So, here's how it works. It's actually very simple for 3 by 3. And we only ever have to worry about 3 by 3 because we can't do cross product in any other dimension. I should say there are 2 ways to do it, but I'm only going to show you one way because in the interest of time. Go down your diagonals. So, I times B times F, what would that be? I times B times F. Yeah, not very profound. J times C, and like, oh, you ran out, Steve. No problem. Wrap around. D, right? J, C, wrap around, you hit the D. So J times C times D, well, C times D times J. All right, you see it? We're going down the diagonals and wrap around. K, hit the wall, wrapping around. AE. So A, E, K. But that's not enough. Now, we're going to do it a second time. But instead of going down, we're going to go up. D times B times K. Well, D times B times K. Now here's the thing to remember. Downhills you add. Uphills you subtract. So minus B times D times K. E, C, hit the wall, wrap around, I. So E times C, I. So that would be minus C, E, I. And last, F, you hit the wall, wrap around, A, J. So F times A times J, so that you subtract it because you're going uphill, minus A, F, J. And now if you say, oh, let me group the I's together, there's BF minus CE. Aha! What about the J's? You got your CD minus AF. What about your K's? You have AE minus BD. So this does give you exactly what you need. So this is good news for us. We're happy. Let's try a quick example together. Our powers combined. See it in action. So we need a vector, which means 3 numbers. What 3 numbers do you want?
7.
Someone said 5, 6, 7. We'll throw them around in some order. We need another vector.
1, 2, 3, 4.
1, 2, and 4. Okay, so we're going to take the cross product. Here we go. We make our matrix, I, J, K. First vector, second row. Second vector, third row. And so, I times negative 5 times 4, negative 20I. J times 7 times 1, 7J. K times 6 times 2, 12K. Any questions on where any of these came from? All right, we did the downs. Now the ups. 1 times negative 5 times K. It's minus 5K, but we're going to subtract that. 2 times 7 times I, 14I, but we're going to subtract that. Notice I'm just writing them so the K's and the J's and the I's are on top of each other. 4 times 6 times J, it's 24J, so we're going to subtract that. And because I've written it so they're on top of each other, we can easily group. Minus 20 subtract 14, negative 34. 7, subtract 24. Negative 17. 12 minus 5. 17. All right. Cool. Now, unexpectedly, this turned out to be a very useful thing for what I want to say next. Well, one of the things I want to say. So we have our vector here. This vector I claim is the cross product. When it comes to cross product, we care about two things, direction and magnitude. Now, oftentimes, it'll be helpful for us to simplify direction, if we can. Is there a way that we can rewrite this vector so it's a little bit simpler to look at? All of these have a factor of 17. So you can pull out a common factor and it's still write that common factor in front. So we're using scaling here. So scaling, we usually talk about scaling, putting a scaling factor in, but of course you can undo stuff. All right, now, quick question. How do we check our work? Because we like points. We want to get all the points. How can we check to see if our dot product is done correctly? Now, we could just say, oh, just do it a second time. But the thing is, if you're making a conceptual mistake, you might make the same mistake. So is there a way to check the output with the input without doing all the work in the middle? Someone said dot product. Why?
The cross product is supposed to be perpendicular to one of those, or I guess both those vectors.
Okay, cross product creates perpendicular things. What does dot product let us do? Check perpendicular things. So, if we took these dot products, what should come out? 0. If 0 does not come out, what does that tell us? Mistakes were made. Let's go fix our work. Now, we don't need to worry about the 17 when we were checking the dot product to be 0. So, minus 12 plus 5 plus 7 is 0. Good news. Minus 2 plus 4 is 0. All right. Good. We know how to take our cross products and check our work. Okay. You should do one. So, here's a question. Find a vector which is perpendicular to both the vector 3, 1, 4 and the vector 1, 5, 9. All right, someone said negative 11, minus 23, and 14. Oh my goodness. That's what I got. Woohoo! Nice. Did anybody notice anything about these numbers? 3, 1, 4, 1, 5, 9? It's pi. That's right. Your math class is being taught by a nerd. What are the odds? Okay. So, we talked about using the cross product, and we can now make the vectors. And so if we're ever asked to find something perpendicular, we're like, aha, cross product. But where does magnitude come into play? So recall that we said the magnitude of u cross v is the magnitude of u, magnitude of v, sine theta. So we have our vectors u and v here. Theta is the angle between them. Now, the thing is that vectors can be moved around. So we can take this copy of v and move it so it ends, so the tail starts at the end of u. And this copy of u, we can move it over to here. So this is also u. This is also v. What shape is this called? Good, parallelogram. Now, how do you find the area of a parallelogram? So the area of a parallelogram, well, the answer is it's base times height. So in this case, let's suppose we make this part our base. What's the length of this side? Magnitude of v. Now, what's the height? It's not the magnitude of u. The height would be if we were to drop straight down. Now, interesting here. Here's our height. We know the length of the hypotenuse in this right triangle. We have this angle theta. In terms of theta, what is this side? It's the opposite. And that side's the hypotenuse. What relates the opposite and the hypotenuse? The sine. And in particular, this tells us that the height is the magnitude of u sine theta. So there's our height. And now we're like, we've seen this formula somewhere before. It's right up there. So our great aha, when we take this cross product, it's finding the area of the parallelogram where the edges are u and v. Well, okay, but maybe I don't want a parallelogram. What if I wanted to find a triangle? Can we do anything about triangles? Because triangles are pretty cool. They have a whole class dedicated to triangles. They call it triangleometry. Could we find this area? Well, you can take this triangle and make a second copy and spin it around. And if you do that, what will you get? You'll get a parallelogram. So, idea. If I want to find the area of a triangle, and I know the vectors for two sides, then the area is half the area of a parallelogram. And we say, well, hey, good news. We already know how to find that. It's 1/2 the magnitude of the cross product. And boy, do they love asking you for areas of triangles. They just do it again and again and again. So let's do one quickly here. Find the area of the triangle. We'll do it together with 1 minus 1 minus 2, minus 2, 0, minus 1, and 0, negative 2, 1 as vertices. We may not do the whole thing, but let's just do enough to sort of make sure we know what's happening. So first off, draw a picture. Does it need to be right? No. It just needs to be enough to get our intuition. So we have points. 1, negative 1, negative 2. Negative 2, 0, negative 1. 0, negative 2, 1. And lo and behold, we have our triangle. Now, what's our plan? We see area of triangle. We just learned we can use cross product. So, how do we approach this problem? Make vectors. Do we need to make vectors? Don't we have vectors? No, these are points. Be careful. Don't try to take the cross product of points. You will not get the right answer. So, how do we turn things into vectors? Well, you pick a corner. Will it matter which corner you pick? No, it doesn't matter. Now, it will matter insofar as it might change your intermediate computation slightly, but you won't change your answer. So, anyone have a favorite corner? Okay. We picked our corner. Now we need to find vectors. And so we say, okay, so if you're finding a vector between points, you look at the differences. So how did I change? Well, 0 to negative 2 tells me I did what? I minus 2. Negative 2 to 0? I added 2. 1 to negative 1? I subtracted 2. Okay, how about here? I went 0 to 1. I added 1. You can think of it as also 1 subtract 0. Negative 2 to negative 1? I added 1, right? Or if you write negative 1, subtract negative 2. 1 to negative 2. Subtract 3. So then the area will be 1/2 the magnitude, 1, 1, negative 3, cross negative 2, 2, negative 2. Now, you can do something I'll point out here. What do these entries all have in common? They're very 2-y. So what can you do? Pull out a 2. Now, what can you do with this 2? Pull it all the way out if you wanted to. You don't have to, but if you like to deal with simpler numbers, pulling out scaling factors can help you. So you can pull it all the way out and then it cancels, and then stuff happens. We'll skip that because I want to talk about a few other things. I know we're cutting short on time. What if we didn't have points in 3 dimensions? What if we had points in 2 dimensions? Is there any chance at all? Or is it like, game over? Can't even start. Can we do anything here? Z is 0. Aha! So, again, in the interest of time, we're not that short of time, but I want to make sure you have enough that we can talk about one more idea. There's this nice idea. 2D lives inside of 3D. So if you're like, I've got great 3D tools, and this is a 2D problem, then you have great tools. Add 0 to your last entry, and then you can compute things. All right, now we talked about areas. Can you do more? Can you do volumes? Okay, so I'm going to quickly explain. We won't have time to do the whole problem, but we talked about how you have this parallelogram, but you can also, that's 2 dimensions, you can think of it as part of a 3D box. This is a parallelepiped. Now, how do you find the volume of a parallelepiped? Or just think, how do you find the volume of a box? Base times height, right? Yes, it is. It's still base times height. So you have U, we have V, we have W. Let's say these are vectors. So the volume is the base, which is an area, times the height. Now, we can find the base because it's a parallelogram. That's really the magnitude of U cross V. Well, what's the height turn out to be? Well, my picture is a little bit hard to see geometrically, but the idea is you drop straight down, and you say, what's that length? Now, it's a little bit subtle, but the punchline is that it's U cross V. The height is the magnitude of W cosine theta, where theta is the angle between W and U cross V. And then you take the absolute value of that. Now, you don't have to remember any of this because there's this really cool punchline coming up. How do you compute angles? Or where does cosine theta show up?
Dot product.
Dot product. So it's W dot U cross V. Absolute value. But that's not even the best punchline. How do you take cross products? What's your tool that you use? You use a matrix. So here's the cool part. Just remember this. If you have to find a volume, what do? You write a 3x3 matrix. But you do not put ijk. You put one of your vectors. Which one? Haha, trick question, doesn't matter. That goes in the first row. Then you pick another vector. Doesn't matter. That goes in your second row. Pick another vector. Well, Too bad, you're forced. There's only one vector left. That gives you a 3 by 3 matrix of numbers. You take that determinant, take the absolute value of it, because it could be negative, and that's your volume. So determinants find volumes. And I know I went really quick there, and I waved my hands a lot, but if you want to go into more detail, there's videos. And with a younger me. So we have, I guess we don't have any time, but there's a fun multiple choice problem. It was B.